This section covers thermodynamics. If you rub your hands together for about 15 seconds, or any length of time, do you notice that they feel warm? That's called thermal energy. Thermodynamics is the study of the effects of work, heat, flow, and energy on a system, movement of thermal energy. All engineers have to use thermodynamics to some degree or another to know how heat or the transference of heat through different materials affects different things. Thermal energy versus temperature. So thermal energy is a kinetic energy. So remember that anytime we talk about energy, we're talking about joules, and it's in transit or being moved from one object to another due to a temperature difference. Temperature is the average kinetic energy of any particle or of the different what makes up an object. It's not the total amount of the kinetic energy. So we're talking about an average. So if we look at the little picture down here, I have a higher temperature on the left side, lower temperature on the right side. Well, you have heat transfer from the higher temperature to the lower temperature. So we have thermal energy being transferred over, and the temperature is the average of that kinetic energy. So a few temperature scales. The freezing point of water in Celsius is 0, boiling point is 100, 32 degrees is freezing point, and Fahrenheit 212. Kelvin is 273 is the freezing point. 373 is the boiling point. So matters are made up of molecules that are in motion, always in motion. So there's your kinetic energy, but you also have an increase in the temperature causes those molecules to have more motion. The decrease in temperature causes those molecules to have less motion. Absolute zero happens when all kinetic energy is removed from an object. So if we talk about thermal equilibrium, right there we know thermal, we're talking about heat. Equilibrium, we're talking about being equal. So that happens when two objects that are touching come to the same temperature. When thermal equilibrium is reached, the system loses its ability to do work. The 0th law of thermodynamics says that if two systems are separately found to be in thermal equilibrium with a third system, the first two systems are in thermal equilibrium with each other. So if I have three items like they show here in the picture, and I have a thermometer, and I know that object 2 and object 1 are in thermal equilibrium, and then object 1 and object 3 are in thermal equilibrium, then object 2 and object 3 must also be in thermal equilibrium. When we talk about thermal equilibrium, the easiest thing to keep in mind, the easiest way to know what you're talking about is if I have two things touching each other, eventually they're going to come to thermal equilibrium. The temperature is going to be the same in both objects. When talking about thermal energy or heat transfer, it's the transfer or movement of thermal energy. And a few of the most common types of transfer, you have convection, conduction, and radiation. 100% efficiency is not, you're not able to get that ever, and then all processes are irreversible, meaning we can't go back to the way it was before. Looking at the first law of thermodynamics, energy cannot be created or destroyed. It can only be changed in form and between different locations. The only way that thermal energy in a system can be increased is by either adding more thermal energy or heat, or by performing work in a system. For instance, we have a bicycle pump. I start pumping that bicycle. It starts heating up on the inside due to the friction. I put mechanical energy into it. We get heat out of it. One type of, that's using the first law of thermodynamics. And the total increase of the internal energy in the system is equal to the applied mechanical energy. The second law of thermodynamics, thermal energy flows from hot to cold, always flows from hot to cold, doesn't flow from cold to hot ever. So if I touch a frozen pizza with my hand, thermal energy flows in what direction? It goes from my hand to the pizza. If I touch a cooked pizza with my hand, first of all I get burnt, but I get burnt because that heat comes to me. It goes from the pizza to my hand. Entropy is the measure of how evenly distributed heat is within a system. typically systems go from an order to disorder. So they go from low entropy to high entropy. So the more chaos there is, the higher the entropy is. And the total amount of energy in a world does not change, but the availability of that energy constantly decreases. So when we think of entropy, low entropy, not a lot's happening. High entropy, there's a lot going on, there's a lot of chaos, there's a lot of movement, a lot of heat transferring. So let's look at convection. It's the transfer of thermal energy by movement of fluid, whether it's a liquid or a gas. So you know that when you heat up any fluid, it expands, it then becomes less dense and rises. Real easy to see this. Throw a pot of water on a stove and watch the steam come up off of it. It becomes less dense, the steam goes up. Boiler heating systems, they were so popular for so long because they would circulate the heat throughout a building without using pumps, but it just allowed the steam to go through the radiators and heat up the different rooms in a building. Conduction is the direct transference of heat from one object to another, from one molecule to another. Their example is putting a metal spoon in a hot cup of soup. It'll feel warm to my hand after a certain amount of time. It's because the soup is transferring its heat directly to the spoon through conduction. So now let's look at some equations. Thermal energy transfer equations in this case. Q equals m times c times delta T. So Q is the energy transfer that we were talking about before, and that's measured in joules. M is mass of the materials. We typically talk about it in kilograms for this, so we need to make sure that every time we deal with this we transfer 2 kilograms. C is the specific heat capacity of what the material is, and that's typically, you find a list for those. And delta T is the change in temperature, going from either hot to cold or cold to hot. So we have a few other equations here, listing them out. P is the rate of energy transfer. We measure that in watts because that's a power. Q is the energy transfer in joules. Delta T is still change in time. We're always dealing in seconds. Thermal conductivity, that's a number that you're given. You generally don't have to look that one. You have to look that one up. You generally don't have to find that one. A is the area of thermal conductivity. So you just find the area of whatever material you're dealing with. L is the thickness of the material, and delta T is once again the difference in temperature. So if we calculate the energy transfer, I take a block of aluminum that's 80 degrees Celsius, so it's nice and warm. I put it in a 1 liter bath of water that's already at 25 degrees Celsius, so it's a little warmer than room temperature. If the final temperature becomes 30 degrees Celsius, I wanted to look for the energy transferred. So I list all my known values. I know the mass of the water, it's in kilogram. I know the specific heat capacity of the water, C sub W, and that's 4184 joules per kilogram degrees Celsius. Kilogram degrees Celsius. The change in temperature, we went 5 degrees. I believe that's a specific, no, that's not the specific heat. No, the specific heat capacity of the aluminum is 900 kilograms per degree Celsius. And the degree temperature change in this case is 50 degrees. So let's list all the unknown values. I don't know Q, which is the energy transferred, and I don't know the mass of the aluminum block. So I select the equations from my previous list of 3 equations. I solve for Q water, and I plug everything in. Plug in all my known values. Tells me the energy transferred to the water. If I want to know the mass of the aluminum, I know QAL lost and I know Q water gained. Plug everything in. Once again using the previous equations that we had. It gives me that the mass of the block, the aluminum block, is 460 grams. Keep in mind through dealing in everything that we deal with thermodynamics, that there's the general, you know that you're looking for different things. This isn't as difficult as it seems. all you're doing is identifying which variables or which numbers go in for which variables, and you're plugging them in. So I want to calculate the energy transfer in a wall. It's 2 meters by 1 meters. It's 0.04 meters thick. There's our thermal conductivity. Opposing sides of the section have a temperature of 10 degrees Celsius and 5 degrees Celsius after 1 hour. So I list all my known values. The area of thermal conductivity is 2 square meters. That's my thermal conductivity, my K. The thickness, we have the change in degrees. And remember, before we said delta T, we were talking about seconds. So I take 1 hour and I have to convert it to seconds, which is 3,600 seconds. Let's list all of our unknown values. The rate of the energy transfer and how much energy was transferred. So I select my equations. I solve the first one for Q. Because now that I have it solved for Q, I can plug everything on the right equation in for P, and it gives me one equation listing everything that I have so that I can get the numbers I want to get. So we have the thermal conductivity, the area, the change in degrees, the thickness of the material, and over how much time. Tells me that I transferred 90,000 joules. So now let's go ahead and look at some U values. These are the same different variables that we were using before. Now we're just talking about the coefficient of the heat conductivity, or how it's the measure of a material's ability to conduct heat, how well it'll do it. We typically talk about in the U.S. BTUs is how you hear those referred to. R value is the thermal resistance of a material. It's the measure of a material's ability to resist heat. The higher the R value, the higher the resistance. You typically see R values when you're talking about just about anything in building a home or a building, but you really hear R values talked a lot about when you're talking about insulation. If I want to know the R value of an actual wall, I take different R values of the different objects, add them together, and it gives me my total R value. Typically, R values are numbers that they give us. So if I look at this, here's a wall. So I go through the 5/8 inch drywall has an R value of 0.56. The fiberglass here has an R value of 19. The 1 inch foil has an R value of 7.2. The airspace 0.17 at 1 inches thick. And then this brick at this dimension has an R value of 0.8. So if I want to know the wall cavity R value, all I do is add up all of my R values. It gives me an R value of 27.7. If I want to know where the R value is at the stud location, so down here, it tells me the R value of the stud is 6.88. So I've replaced the R value of 19 with the fiberglass with the stud, and I get an R value of 15.6. So I get a higher R value out of my fiberglass than I do with a wood stud. So another type of thermal energy transfer, radiation. It's the process by which energy is transmitted through a medium, including empty space, as electromagnetic waves. Think of the fact that standing out in the sun, you get warm. That's radiation. When you talk about energy transfer, Stefan's law is that all objects lose and gain thermal energy by electromagnetic radiation. Here we have the radiated energy transfers, my P net. Stefan's constant, it's the same. It's a constant. It never changes. So when they talk about Stefan's constant, this is the number we're always talking about. A is my area. E is the emissivity constant. Once again, they give you the number. It's a number that never changes. And then T's are our temperatures in Kelvin that we raise to the 4th power. This is an area, when we start dealing with these types of numbers, you have to be very careful about rounding. Because if you round the number too soon, and don't try to use the whole number, you get a very, very different number than what you had intended. So I have the final temperature minus my initial temperature, both of them raised to the 4th power, times all these other fun numbers. So if we talk about thermal energy transfer, so prior to dressing for school, a student watches the morning weather to decide what clothes to wear. If the bedroom's 65 degrees and the student's skin is 91 degrees, 91.4 degrees, determine the net energy transfer from the student's body during the 15 minutes spent. watching the morning weather. The skin emissivity is 0.9 and the surface area of the student is 1.3 meters squared. So let's list everything we know. Area is 1.3 meters squared. The emissivity constant is 0.9. Stefan's constant never changes. It's 5.6696 times 10 to the negative 8. The bedroom temperature was 65 degrees. Skin temperature is 91.4 degrees. And the change in time is 15 minutes, which I convert to 900 seconds. So I list all my unknown values. I don't know the rate of energy transfer. I then need to select equations to solve. There was only one equation we've used thus far. So Q equals P times delta T. Apply all unknown values. Solve for the two temperature differences. Remember, they have to be in Kelvin. And then here are the numbers that they plug in. Remember, raise them to the fourth power. Here's their number. This is them converting it. Remember, times 10 to the 9th is giga. I continue working through. Just being very careful that I don't round too early and I plug in the full numbers into the calculator. I plug everything in together. I get 93,500 joules is how much energy was transferred from the student to the room. Applications of thermal energy. Solar collector assembly pulls in heat. Here's some other examples of that. We've seen this one numerous times. A way to boil water. Converting solar energy directly to electricity. It's another way. Geothermal energy. They take heat from the Earth's core, use it to boil water, do a variety of things. But geothermal energy also refers to taking heat from the atmosphere. This section is not as difficult as it seems. Like I said before, it's a lot of plugging in values for variables that are there. Doing some conversions when it comes to the metric system or the SI notation. My suggestion is you go through, do exactly as they show you. List all your known values, list all your unknown values, select your equations, and go from there.